So we'll start with Dr. Jaising.
So, good morning everyone. I welcome you all to the first session of the second day. The first talk is by Dr. Jaising from Guru Bhaskar University. I welcome him to the talk.
Okay. Thank you very much, Chairman. First, I would like to thank Professor Anurag Srivastav and his team, organizers, and students. See, this is not a scientific talk. This is my personal view as well as the motivational lecture as you. After the invitation of the Professor Anurag, and we have discussed a lot of things about how to succeed this conference, and we have planned to publish some work in some international journals and other during our conversation, Professor Anurag said he wanted to invite my supervisor, Professor Owen Srivastava, and but could not. Then during this discussion, we have decided we have organized one session on the memory of the Professor Owen Srivastava. He is a legendary scientist. So today I will discuss about his work and short, and then I will discuss about my own. Okay. Basically, during this talk, I will discuss about I will cover two topics: hydrogen and synthesis of zinc oxide. Yeah. Professor Srivastava, he was born in 1942 in Banaras, and that he was a legendary. He got Swami Vishnu Bhatnagar and Padma Shri awarded, and you see his supervisor was Professor Ajit Ram Verma. He is a very renowned and he was director NPL more than 25 years. Yeah. He has awarded several awards, and more interesting things is I want to say here. All awards he was received after retirement. That is very interesting thing. All more rewards after retirement he received after 65 years, and that 1988 he was received the Shanti Swarup Bhatnagar and the High Temperature Superconductor, and that is very renowned work he did in this area. And he is a research in the hydrogen production, hydrogen storage materials, hydrogen fuel devices, nanomaterials, especially zinc oxide, titanium oxide, quasi crystals. He did a lot of wonderful work on quasi crystal. He is especially on the structural and correlation, property correlation work. And high temperature superconductor and CMR, multi-fluid, carbon nanotubes, carbon nanofibers, graphene, polymer fission, biomaterials, drug delivery, and layered. And most important interesting things is he started many work after the retirement. That graphene was discovered in 2004 and he was retired. And he did very wonderful work and particularly in graphene. Okay, and he has source of inspiration for the researcher, teacher, and scientist, and all about the wonderful human being. Basically, I have a lot of story. Basically, you can say I'm a lovely student of him. So I have a wonderful story. His passion, his strengths, colleagues, and collaborator for research and science technology. He was very helpful and supporting to everyone around him, but never compromised. The most important thing, he have a bigger group. In a group, more than 30 to 35 PhD students and more than 30 to 35 people working behind him in a different and as like Pune, as like some supporting staff, as in more than 100% doing in his work in a university system. That is very important and interesting. And he never said no to any type of work and challenges thrown him, even at age of 50 years. And continuously, he never left BHU and his lab after joining BHU as lecturer 1965, and besides getting many lucrative offered admission, I think he got several opportunities for directorships as well as vice chancellorship. Never he accepted. And more interesting things, in every Deepavali, he visited the lab and lighted the lamp. And that is important thing कि उनका कहना था कि जहाँ की रोटी खाइए वहाँ की पूजा सबसे पहले अदर बातें बाद तो ये चीजें बड़ी that is very interesting very memorable things and always encourage to all the students and that is very important and that is they give the wonderful supervision and that many things yeah in 1965 2016 he is awarded for the fourth civil action award. This is a Padam Shri, and 2020 he was visited my place at Sagar, and that event is completely organized with the help of in respect to Ravi Pandey sir, and that is the whole supported by Ravi Pandey sir. And during the visit of the I think hang. Hang over here.
Yeah. Actually, this moment they want to capture. We want to.
Yeah.
Oh, yes, okay.
Okay. And during the I think this is a picture taken from the when the APJ Abdul Kalam visited our lab, and he is appreciating the all in all respect. He is given the name the hydrogen man during his visit, and he cited his work several times during the Science Day and many platforms. Professor Dr. APJ Abdul Kalam has said many things about this, and there was I think Professor C.N. Rao and Chidambaram some visited continuously, and every 2 years he visited to, and I think I went to several times to work on him and say, okay. I think this guy is right now is K. Rasulurangan. That NEP 2020 is the whole soul in charge of this. Okay, this is another renowned guy, Ashok Sharma, and Professor Srivastava was an institute builder and team builder and visionary and dreamer. And in all respect, his popular statement like, research is like finding a needle in the dark. That is very important. And every time Professor Singh Rao said, ये दुनिया ना गोरों की है ना कालों की है ये केवल दिमाग वालों की है जो मेहनत करेगा वो बढ़ेगा अदरवाइज नहीं और आज भी सिंह राव सर कंटिन्यूअस को लैंड अभी मैं लास्ट ईयर में उनसे मिला था वो अर्ली द मॉर्निंग 8 AM पे वो अपने लैब को जाते हैं 2 hours वो लिखते पढ़ते हैं फिर देन वो मूव फॉर द बाकी अदर सेस और दैट्स द वेरी लेट okay more than 100 crore projects brought by own Srivastava by their own effort that is very interesting and he has developed a major research facility at BHU synthesis instrument. In synthesis instrument we have the PLG deposition system, sputtering system, more than 25 high temperature furnace, high quality furnace, and more important things, we made the several furnace by own resources, own hand. It always encouraged to all students to prepare some model, some design or system, and then you go for your research. And characterization techniques during my journey, we have the 2 HRTM and 200 kVA and 300 kVA, 2 SCM and XL20 and some Philips, I think. Okay. That another setup, Raman, we have with 2 different sources and property management, a lot of system we have in respect to superconducting devices and many more. And application point of view, he did a lot of hydrogen storage. Yeah. So this is I think always he was leading 2% scientist and Stanford, and also more interesting thing, more than 10 students is listed in this. Myself also listed in this list. So, okay, his work is more than 75 publications, and he supervised nearly total 75 students, and both are all are doing very well and excellent all over the world and India. Okay, and he this is some publication details and research, And I think many people know about this wonderful book. This is one of types of some Ramayana in respect to crystallography. Still, family got a very good amount royalty amount family receiving. So that is one of the more interesting things. And that if anybody doesn't know, I recommend please read this book. This is a wonderful read. And that book was written in 1970. In 1970, it was written in that. Okay, and some other Professor Ahuja is also collaborated with sir for experiment of this hardware storage. Automatica will give some. Okay, this is another work. Basically, the Indo-Sudan research, doing the Indo-Sudan research work that will be published in some. Okay, please on the video. The one short video, I want to show what is the actual ground level reality. Yeah, this is the group. I think only hydrogen group, there is not the whole group. There is several part. Nano group is alone, and different hydrogen groups is different. Superconducting group is there. There are basically 3 and 4 types of groups there. Yeah, and these focus all aspects of hydrogen storage. Technology development used not only for transportation and 2-3-wheeler and also house. Important the air conditioner and cooker system, electric generation, and they have been close to concept of hydrogen house. Please go. Yeah, this is the hydrogen house. That is, I think we have developed during our PhD. And please go in the last 2 minutes. Yeah, this is the hydrogen tanks. I will explain our. Next. Yeah, this is a 2-wheelers. I think the they were drawing. And the more important thing is, more interesting thing that after that we have used this hydrogen vehicle, there is only water, nothing else. Yeah, it's the 2-wheelers in front of Lanka, is in front of Yesu gates, and that is continuously that Lanka gate to 80, this Sonar region, that is one of the most important things. City, please go last. Yeah. The other that also he made the home cooker for that mixing of some methane gases, and also that is not pure hydrogen, but mixing of some other hydrocarbon with then there. Yeah, please complete this. Next slide. Please go to slide. One per slide. G. Okay. Why I am talking about the hydrogen storage? Basically, in the study we have listened very wonderful talk about the hydrogen storage, how to clean the water and water splitting, and that is a lot of problem. Basically, we need too much effort for the especially on this topic. Basically, that hydrogen is abundantly available in the complete renewable source, and that is pollution-free energy source, and that can be stored and transport, and also can be replaced the petroleum gasoline. That is one of these category. Due to that, we are that is useful for, and also hydrogen property is very good compared to any methane and any petroleum there. So due to that people are thinking about this. And as we know, this is the first element in the periodic table, and that is 3 types of isotope is available. That easily is a hydrogen and oxygen is connected and then found of H2O, and the same that is reversible process. And hydrogen economics is completely dependent on 3 pillars. That more important is production, storage, and application. And steel production is very costly, and that nearly $2 for the if you want to generate the hydrogen from ground. That is one of the things, and my supervisor Basically, he used titanium oxide for producing the hydrogen by only the some splitting water splitting system. Yeah. Please. Where to store? How to store the hydrogen? Basically, there are three types of the storage possibility. Compress the high pressure storage wide that and liquefaction this system are more interesting and more safe the solid state system. The most efficient hydrogen atom is stored by the state hydrogen stored material like binding S2 and chemically and physically both chemical absorption and physical absorption methods, but we prefer chemical absorption and he did a lot of work in this work. Okay, this is you can see here there are three types of storage system, and third one is there is some metal hydride. They put in this there in ammonia tubes and put in some they get a lot of work in they have developed more than 25 types of different materials and they're used for the application point of view. And this is wonderful review articles that in a hardware storage engine involves in Indian constraints that you can read the all aspect of and the Indian scientist what he did and what is going on. So that is and he did and about the hydride material, complex hydride, intermetallic, porous carbon, and so some structural model of this hardware industrial materials that is FeS2 and sodium AlS4 and that is also carbonate groups and fluorine and that. But there is other types of system that he is focused on some intermetallic metal hydride that AB3 types, AB types, A2 B types, AB type, BCC type, and that magnesium hydride, ammonium hydride, some storage high specific surface porous graphite carbon, and that also calculate and some other new types of carbon nanomaterials. Yeah. There is some DOU that is given by the Ministry of the USA and Department of Energy USA. And basically, right now they have set the new target is of only 5.5 weight percent enough for the hydrogen storage. If any material is stored at 5.5%, that release the hydrogen. That is very important. Release hydrogen at room temperature at 1 atmosphere. That is good for that. This type of material that we have, I'm going to discuss about here. MS. Two types of material. That is, this is one type of chemical system. That here you can see there is some wires. In wires, hydrogen molecules break and hydrogen ions, and that hydrogen is sitting in the wires, and that then that some special types of some reactor and other thing. And after that, we given some temperature and pressure that hydrogen will release and liquid and then form of hydrogen. So this is the formation of this intermetallic hydride. There is you can see here the wires and that wires is completely that is basically hydrogen atom is very smaller that can sit anywhere and that will absorb interdistinal sites and many positions that will be and that more important to release the hydrogen is very complex and many material can absorb the hydrogen but cannot release the hydrogen. So that is one of this process. They have absorbed and desorption is more important in this mechanism. So for this, there is some this is not my work. This is the work of my friend. The object of his work is that find out hydrogen, basically 85 types, and that he has tailored the material by the doping of iron and magnesium, and they want to replace. And especially and early and find only hydrogen absorption 1.4%. When we replace by the iron, that is hydrogen storage capacity is nearly 1.8%. When we blow the nickel and then that storage capacity is 2.1%. But we use the 50% iron or nickel, that storage capacity is nearly 2.4%. That material BHU has used for the demonstrate the ore vehicle. So in our vehicle we have used this wonderful material. This material is at a room temperature that will be liberated and at I think it's nearly 10 atmosphere. Okay, how to possible way to tailor this hydride material to improve the hydrogen storage? This will tell you through the substitution of the high electron. Basically, we are focusing to how to increase the cell volume. Then, if you increase the cell volume, that easily that can absorb the more hydrogen, and that is very important. And that also telling the based on electromagnetic radiation and telling to the this substitution considering combined effect of size and electricity of the this substitution reaction. So this is some simple things that we have basically more important things, and sometimes is the oxide material is very tedious, but especially on lanthanum oxide is doing good for the as work as a catalyst for liberating hydrogen. So that is very interesting. His group is developed several catalysts for the especially lithium, palladium, and also carbon nanotubes for the work as a catalyst for the formation. This is basically in 85 types. There are 37 types of wires, and in this there are 3 types of octahedral and cell, and nearly 34 types of tetrahedral wires. And basically, only 6.7%, 6.7 wires is filled by the 1.4%. So anyhow, if you use the whole wires, that will be good for the storage capacity for the this, and that is if you do something, then how to liberate this hydrogen, that is very important. And then there is his group has opted, there are 2 techniques. There is ball milling techniques as well as RF indexing techniques, and that uses very large, I think, the furnace for the for melting and this. After the synthesis, they move for the compression, and then by the there's XRD system, and there is some FECM and Tech9, and basically my training is in the FEI and the boost system. He are trained to me and all this trend, and in all respect for the for during my PhD. Yeah, this is experimental protocols, and that for this we have used the iron and nickel, iron 0.9% and yamian and 0.1%. So the same observation, we have changed the ratio of iron and nickels, and then finally we found that this is then at different temperature that will the system will be absorbed and hydrogen nearly 2.4 weight%. So the whole absorption kinetics, you can see here that the system will be time versus the absorption release, how the system different composition is released. So in particular, in the when is used 0.5%, we got the 2 weight% hydrogen can be released by this system. So basically here this is simple thing. When you do with basically a larger size of iron and yamian, that will be increase the volume size of this unit cell, and due to that, then the system will be stored the more hydrogen, and that at the root of this easily. Basically here nickel is a work as a catalyst for the transformation of the release the hydrogen. Here, this is some microscope. Yeah, this is the mode basically that already we have seen in during the video. So how to use this system in the back side of this nano cards, and this is the hydride tanks. This hydride tanks is made by very simple. Only weight is of this hydride tank is 10 kg, and we use nearly 20 to 25 kg material for the storage, and that more than I think 100 gram is enough for 70 kilometers for that will be used for this. So there are a lot of things about in this one. So right now I'll move in my own one. Yeah. Yeah. Okay. So during my PhD, I did work with Professor Hans Swasta, especially on zinc oxide, and basically this material is the old material, and basically for scientific community, not for the application point of view. So a lot of competition already. I'm doing a lot of good work on this work, and I found a lot of presentation during this conference, especially on zinc oxide, and Professor Kuswaha is a wonderful talk on the general TiO2. So that material used for the various application and in this, especially on the industry, we know very good material for this is the cosmetic material for the that is biodegradable material. So that material, why I am discussing about zinc oxide. Thusly, we have developed the very different types of nanostructures. Only help the very simple techniques. We have adopted the backward deposition technique. With the help of this, we found the various wonderful structures we have developed, and that one is controlling the flow of the argon, oxygen, and amount of the zinc. The zinc is melting point is very low, nearly 400 degrees centigrade. So we no need, and that for this we have. So motivation of this work is different. Motivation of how do this zinc oxides grow different type of nanostructures, and this and we have grown this align nanoroid without any substrate. That is one of the wonderful work, and that after that we have listed the Pune city for the field emission property, and also that another what we did the magnesium dope zinc oxide for the hydrogen storage. I am also going to take some small work in the hydrogen storage, and then further. So I want to discuss about this, especially about structural hydrogen and study of the hydrogen and magnesium dope zinc oxide. Okay. So for this, as I told you, we made the own hand by design the furnaces. And this furnace we have designed red. And that we are using the argon and oxygen, argon as a carrier gas, oxygen as a reactive gas, and with the help of we are using the high carrier flow rate. Thus, different structure we find at 100 SCM, 200 SCM, 400, and times. He insists to all students, please go to the lab, do one experiment daily. उनका हमारे लिए एक इंस्ट्रक्शन था या डायरेक्शन था कि हर स्टूडेंट को एक एक्सपेरिमेंट जरूर करना, और वो ऑलवेज हम लोग जैसे वी हैव वेरी गुड लैब विद रिच फैसिलिटीज, सो देयर इज नो मेनी वी आर अवेलेबल SRD in an hour you can do SRD, DM, any work you can do, any types of prediction. So we have we posted the zinc oxide that is cotton like basically. For magnesium dope, we have opted the two-step process. First, we grow the zinc oxide nanowires, and after that, we have used the magnesium dope. In magnesium, because magnesium is easily oxide, they make the magnesium oxide. So we use the tantalum tape for then we make some billet, and billet will be covered by tantalum, and that used for the in a vacuum, and we have used one is 600 degrees centigrade we have used for the Elding. That further we use for the filtration as well as they use for the hydrogenation process. So this is I use for the SRT, and that we for detailing for this we get the rate refinement that we find that then that our system is volume is going to increase when we dose the 10% 10 atomic weight per square or magnesium, and then we especially focus for the only 10% for the hydrogenation and other property. So that you can see here, this is the TM and HRTM, and that system is easily available for all the students. You can go and that you can take the photographs and you can discuss with your supervisor, and then that is important. Yeah. So you can see here the hydrogen absorption kinetic, and especially when we took the 10 weight percent of the magnesium, then we got nearly 100%. That is not good for it, but people are reported nearly 2.4 weight percent in this system, but we got only 1%. And then when we increase the magnesium, that is nearly 0.8% only. So that is not good, very increasing, but we got anyhow good publication. That is that. So, yeah. So the PRA spectra, I don't want to. Yeah, this another one I want to. How much time? 10 minutes. Okay. No, I will. Okay. This another one. This in this work we have developed different types of microstructure control. That is very important, as you know, in a nanostructure, how to control your system. by the chemical method, by the physical method. So I found only PLD and sputtering techniques is good. I'm not criticizing to anybody. If you go for the chemical method as well as any sometimes tetrapore, sometimes tripore, sometimes nanoblockers. I was too much hopeless, and when I was used the PLD, then and then sputtering. There's two board techniques. Sometimes CVD for especially for the different, but not for especially for the zinc oxide. If you use for CVD, So for the detailed structure, we have used the HRTM and also this is nanoflower, and behind the reason of this find out there is basically we have not used catalytic for the formation of this. So ZNOX there is for the formation of this different type of nanostructure. So we did a lot of things. So right now time is over. So I want to quick. This is one of the recent work that PhD work. Recently we have published. Okay. Acknowledged my supervisor as well as the Busan Institute, South Korea, Sejong University, Cologne Institute, Germany, and DST. We have nearly 3 projects from DST and 2 projects from UGC and Department of Physics, Dr. Harish University, and 4 applied physics BHU. And these are my collaborator. And this is my citation, nearly more than 3,500 citation and 100 self. This is the area of my interest. Recently, I have started area and biomagazine. This is my recently. Thank you very much, organizer. Especially, this is some wonderful we have set up in our resource. Everybody can come and that use this is a national accelerators. Yes.
Thank you very much for the nice talk, and we have time for a quick question. Professor Ahuja is online, so therefore,
yes.
मैं और मेरा ऑर्गेनाइजेशन आपकी क्या मदद कर?
सर हम लोग बात करेंगे, हम आपसे मिलने के लिए ही आ रहे हैं, ये नहीं बता रहे हैं इससे डिस्कस करना है मुझे आपसे। बात सर आपसे कई बार पूछ चुका हूं सर। Any further question then? Yes.
When you are changing the different form of zinc oxide nanostructure, are you trying to change the physical parameters at the sidewise, or you are using some other techniques what you were trying to refer?
Basically, more interesting things, we are not using several things. We have used only the argon and oxygen flow.
Okay, so what was the flow rate?
Only flow rate. And we found the various types of structure. So sometimes we found the nanocombs, nanoportals. I cannot say this type of nanostructure, wonderful structure, but especially control manner, we have found only 2 structures, nanotetrapode and nano. And other structure, some structure we have not repeated, so that I move for the PhD, discussion for PhD.
So why do you think those structures are not coming up in form of uniform or controlled manner?
Basically, that is not too much control manner. Basically, we are using the silica tube. Silica tube is diameter is nearly 4 centimeter, and also we are using the some zinc powder. Amount of zinc powder is also playing a crucial role in the formation of this. So there are a lot of things in the but we want to deposit some on substrate and other things. In a substrate is okay, but that system of deposit on silica tube, that we found the different steps.
So what causes those already
Basically, causes behind the that system is not too much control. Basically, the oxygen pressure and organ pressure. Basically, we are using very long tubes, and that is not that system is not equated by the controlled by the some I think CVD like CVD and other. That is open tube system.
And why do you think that it is not possible chemically to generate uniform or monodisperse structure?
Basically, same thing is the role play the pH and pH temperature. Basically, that material is very sensitive. I did in the magnesium, we found a wonderful nano, I think, hexagonal patterns. When
I think we can continue this discussion during the high tea, right? And so we have privilege and that we are happy that Professor Rajiv Ahuja is online. And so though he was supposed to be with us yesterday in the morning session, but due to his other commitments as the administrator, as the director of IIT Rupert as well as IIT Guwahati, and it was difficult for him to travel to Gwalior, and but he has accepted our invitation to be with us through online mode. So I welcome you, sir. I welcome you, sir. Can you hear me?
Yes,
Yeah, great, sir. Great, sir. So thank you, sir. Professor Rajiv has been my mentor as well, and during my postdoc, and we are connected for the last more than 20 years so far. And for because we decided to felicitate him for his contribution. If you remember that yesterday I read the citation of Professor Rajiv Ahuja, and to read the citation of Professor Rajiv before he started his keynote talk, I invite Professor Abir. Abir has also been part of the same group, so I am just giving this responsibility to Rajiv, to Abir to read his citation.
Yeah. Well, it is a profound privilege for us to have Professor Rajiv Ahuja here in this conference as the guest of honor and the keynote speaker, even in the online mode. And personally, it gives me immense pleasure to introduce Professor Rajiv Ahuja, who happens to be the postdoctoral mentor of Professor Anurag Srivastav and myself. Professor Ahuja is on leave from Uppsala University, Sweden, and has been serving as director of IIT Rover since 1st of April 2021. He has taken over the additional charge of IIT Guwahati on 7th November this year. So currently he is the director of 2 IITs. Professor Ahuja is one of the most highly cited researchers in Sweden and India. He has been listed in the top 5 material scientists in India and Sweden. Professor Rajiv did his PhD in physics from IIT Roorkee in 1992. In 2021, he has been awarded the Best Alumnus Award from IIT Roorkee. So he joined Uppsala University, Sweden as a postdoctoral fellow in 1992 and gradually rose to the rank of professor at Uppsala University, Sweden in 2007. So he has returned to India after nearly 30 years as the director of IIT Roper. His research interests hover around energy and high pressure physics. He has published 1083 scientific papers and has garnered H index of 99 and more than 45,771 citations. These numbers increase very rapidly. More than 100 publications are in high profile journals such as Science, Nature, Nature Materials, PRL, and so on. Professor Raji has supervised 30 PhD students and more than 35 postdoctoral fellows, including myself and Professor Anurag. He is a fellow of the American Physical Society and Royal Society of Chemistry, FRSC UK. He serves as the associate editor of the Journal of Nanoenergy and is on the editorial advisory board of Journal of Materials Chemistry A and Materials Advances of the Royal Society of Chemistry UK. Beller lecturership was awarded to him in the APS meeting 2017. He is a fellow of the Royal Swedish Academy of Sciences and recipient of numerous prestigious awards such as the Wallmark Prize, the Eder Lilly, Sven Theras, and the Benzelius Prize in Sweden. IIT Roper is shining bright under his brilliant leadership. He has raised IIT Roper to great heights in less than 2 years. And on a personal note, we found him to be a very friendly and a cool mentor. And in the warm atmosphere of his group in Uppsala, Sweden, we were able to deliver our best. Without any further delay, may I request Professor Rajiv Ahuja to deliver his keynote lecture. First of all, we would like to, may I request Professor Anurag Srivastav to felicitate our beloved mentor, Professor Rajiv Ahuja, and then he will deliver his keynote address speech.
But I'm not in the market anymore. Thank you, thank you. I will take when I will come there. Thank you for your kind gesture and Abir, whatever you know, Abir, and what Anurag has done, that was wonderful. And I'm sorry I could not join. Can you listen to me?
Of course, sir.
So this is my office in IIT Guwahati.
Now can you start your
Oh, can you see my screen?
Yes, of course, we can see that. Yeah.
So, thank you, Anurag, for this invitation, and I feel very sorry I could not make it. And when I say yes to you, that at that time I was not having charge for IIT Guwahati. So, so this is how the life is. So it's very hectic. So I could not make, but I was sure I would like to come to Gwalior. And so, Abir, thank you for my kind introduction. So I will talk a little bit about what is about the Indian hydrogen mission, the national hydrogen mission of India also, and why hydrogen is so important that there are many countries are looking for that as an alternate, and India is also going all the way for hydrogen. So this is the future, not only in Europe or US, but also in India. So I will talk about energy application and where how we can use in computational materials science approach uh, to address those issues. So this is our entrance at IIT Rockford actually. So this is how it looks like in the night. And now I'm also at IIT Guwahati also. This is if you have been to Guwahati, Guwahati is one of the most green campus among IITs. So we have in the campus, we have a one hill, we have a lake, we have a river. All three things are inside the campus. So it's a very green campus, and IIT Guwahati was set up in '94, whereas IIT Rockford set up was in 2008. So in that sense, IIT Guwahati is a little bit older institution compared to the IIT Rockford. So I have a chance now to compare these two institutions. How does old institution looks like, and how does the new institution looks like? What the difference between old and new institution? Of course, I still hold my position at Uppsala, and still working there. I'm on leave from there. I took a leave for 5 years, and I joined here as a director at IIT. When we talk about material research for energy application, we talk many areas. We talk about power generation, so you can see that a lot of people are working, for example, fuel cells or photovoltaic. And then we talk also about transmission, which nobody thinks too much about the transmission. And if you look at that, the power losses in India and even some places in Punjab, it can go up to 20 to 30, almost 80% or 70%. We are losing in transmission. So if we can save those losses and if we can improve our transmission wires, for example, if we can make those wires with a superconducting material, then we can get rid of all these losses. And the losses which we are losing now 70 to 80%, some cases 50 to 40%, you can save those losses. And saving energy is also producing energy. So when I talk my colleague in Sweden, they are working in ABB. So they always tell me how you can reduce the power losses. And same thing is also the transformer. So if we make a transformer using the superconducting wires, so we can again save a lot of energy. course, when we talk about consumption, we are using nowadays solid state lighting. So we are saving energy in that term also. That is, so we design any material for LEDs and then we are saving energy. So saving energy is also reducing energy. So we are also working on the storage when I will talk, which I talked about today. So basically, I will talk about hydrogen storage and batteries, but we are also working in superconductors and supercapacitors and other class of storage materials. So advanced materials are useful for our sustainable, what we call the development, or we want the sustainable energy resources, or at the same time there should be the green also. So you can see that there are a lot of things has to be done. And I want to tell you one thing that in India we are not putting too much efforts on the material research. And if you go to any IITs and you can see that all the students they want to go to computer science only. And you can see that when we have this JOSA, which we call this IIT ranking, when they get student get admission after JEE advanced, they all want to go to computer science. And if you go to any IIT, the lowest ranking goes to the Department of Material Science or Metallurgy. So we have to change this trend, because if they, and as our Prime Minister always says that we want to be a third biggest economy in the world. So we have to develop our manufacturing sector. You cannot have manufacturing sector without materials. You cannot just run software. To run software, you need a hardware. So we have to put a lot of efforts on the material production. And when we have this kind of conference, this kind of conferences give us they create a collaboration. So where people are coming from different part of the world, different part of India, and they sit under at the same umbrella and they can talk and discuss. So what I'm seeing since I joined here, I see that the collaboration part is very much missing here. People doesn't want to collaborate, and they don't want to collaborate within the institution and forget about other institutions of the country. So we have to create that kind of culture that they should collaborate, and especially when we talk about multidisciplinary research and interdisciplinary research, collaboration is very necessary, very important, because you cannot be expert on everything. So I give always this example. This example is from Uppsala, and I shown these two pictures. One on my right hand side, picture of Professor Anders Celsius. So he was a professor in our department in 1730. And on my left hand side, you can see the another professor is called Monlini. So he is a guy who has given the classification of the plant. So whatever classification of plant exists right now, it is given by Paul Monlini. He was a professor of medicine around the same time. And one of this conference, they meet together like you have this conference today. And then Vinny suggested to Anders, I heard that you have given a temperature scale. Your water is boiling at 0 degree and freezing at 100. It sounds very awkward. Why don't you revert your scale there? So Celsius got this idea from Lenny and he went back to his lab and he reverted the scale. Think about it. These two people, one guy from physics and one guy is from medicine, they don't have. We will still using a temperature scale where water is boiling at freezing at 100. So this is how important is the collaboration.
Sorry to interrupt you, Rajiv. You're on which slide? Actually, we find the slides are not moving at our end. Actually,
Is it?
yeah. I think we are still on slide 1.
You are still on slide 1?
Yeah, it seems on the title slide.
So now it's moving on.
It's still not moving. We are stuck at slide 1.
Okay. Okay, I will try to do it again. Okay. This is that the slides are moving on.
Yeah, can you make it full screen? I mean, if you go to screen share mode, if you share the screen,
Okay.
yeah, I think that will work.
So now you can
Yes,
see.
yes, now we can see. Yeah, please go ahead. Yes.
So when we talk about Indian situation, how important is the hydrogen mission? And this is one of the speech from our Prime Minister Modi, and where he talked about the national hydrogen mission to make India the global hub of the clean hydrogen and it's the biggest exporter. So you can see that the Prime Minister is when he talked about the Gati Shakti program, hydrogen is a key here in the Gati Shakti program. So the government of India has decided to open many hydrogen valleys in the country, and this is one of the initiatives which come also from the Department of Technology in India, hydrogen valley platform in India. So they are going to set up around 7 platforms within India, and which are focused on from all the way from hydrogen production to storage and to application. So if you can see that in Indian scenario, right now we are all using hydrogen gas for hydrogen for using hydrogen in mobile application, for example, in the buses or in trucks. So the idea is that how we can make these cylinders safer. Another thing is that because we don't want to build a hydrogen, because we don't have an ecosystem hydrogen filling station. So we want to have a cylinder where we can go up to very long distances. So there are two kind of work are going on, especially in IT that we are designing a new kind of hydrogen cylinder. Of course, we want to have this cylinder should be small and compact, and as well as the materials point of view also that it should be very safe. Because in these cylinders we use hydrogen under high pressure. So right now we are using 200 kilobar. So now if you want to make a really big cylinder, so then people are thinking going up to 700 bar, so 700 bar pressure. So right now you're using 200 bar. So there is a research going on production also, and how we produce the hydrogen. That is a key issue also. And for example, for Punjab, we are going for with the biomass because you know that Punjab has a lot of this biomass when there are a lot of cases also you heard and you know the pollution is coming from Punjab or this Korali burning. So we want to do that Korali produce hydrogen and we want to produce a green hydrogen. So that's also right. We don't like to use a gray hydrogen, black hydrogen. We want to protect. So there is a lot of effort. So when we are going to develop this valley and Copper, so basically we will use the hydrogen from biomass. So, we want any of these economy, it should be a sustainable. Can you see up here now? Hello?
Yes.
Can you see?
Yes, Rajiv, we can see. We can see.
Okay.
Yeah.
So we talked about hydrogen economy because hydrogen economy is a sustainable economy. Why is it a sustainable economy? Basically, what we do is, if you take just simple water, you break water into hydrogen, and then we can store hydrogen in some media. It can be solid, it can be liquid or it's a gaseous form, and then we can use, for example, in users. And then once byproduct again, you will get when we use the future again hydrogen. We start with hydrogen, get hydrogen, and this hydrogen recombine again with oxygen in the environment and produce water. So in that sense, basically you start with the water to end with the water. So this is the circular loop and this very clean loop. So hydrogen can be stored in three different ways. We talked about high pressure storage where in cylinder you can put hydrogen under pressure, then you can have a liquid storage also where hydrogen can be cooled down at the cryogenic temperature. And then we have a solid state storage available. So most of the work in India is doing now is a gaseous storage, which is not very safe in the sense because hydrogen is under pressure. So basically, then safest way with the hydrogen. So we will talk a bit about. So this is how the community hydrogen in that we fill our kilns with the water only, and then we go up around the world. So this is our wish, people working in a hydrogen economy area. So we don't need any oil or gas, we need water and fuel, water in the plane, and we produce on board, and we go around the world. The other aspect here of the batteries, for example, and the challenge in the batteries also that we need a very high capacity battery right now because we want a lot of application in our laptops or in mobile phones. So that are driving that we need a high capacity battery, but when we want to use this battery for mobile applications like laptops or your phone, we want very lighter batteries. So battery should be thin. So you can see that if you look at the on the right hand side that we want very thin battery at the same time very high capacity or a very high density battery. So this is also again a challenge. So where again material science will play important role and computational material science help to design those kind of materials for the battery application. And this is the you all know that good enough to other people Nobel Prize for this battery, but we are using in our mobile phone this week and over the So this is recognized by also the Nobel committee that batteries are used everywhere. So usually if you see the Nobel Prize are not given for the most technology development, but for the basics. But this was gone beyond the basics. People are nowadays nobody can live with batteries. So this is the this is about invented and they got no place in the things. And when we talk about computational material science, we always think that if you want to be able to experimentalist, you should be able to theoretician. So this is one application which I say that I took it from Da Vinci's novel that practice should be always based on the sound of this theory. Otherwise, you are going in a state without knowing direction. And when we talk about computational material science, so we are talking in electronic structure, but some of quantum theory, and now everybody in India, all over the world, we are talking about quantum mission. We are talking about quantum computing. So, how important is all of a quantum theory or quantum mechanics? You can see that it's a wide future application. So, if you look at this history of the quantum theory or electronic structure calculation, basically what we are doing is from last century itself. So there are a lot of progress was made, and so thanks to the density function theory that we can read nowadays a lot of these complex system and multi-million atoms and through that ways. So that's the way how this field grown and now we can make a prediction which can be plus and we can easily convince our experimental models. So when we talk about, as I told you, we talk about hydrogen, when we talk about storage for mobile applications, we are always concerned about the weight. We don't want to have a heavy weight materials. For example, if you want to drive this car for 500 kilometers, so you see that, and the size of the tank, if you put in a 200 bar of pressure, this is the size of the tank. And but if you go to the liquid storage of hydrogen, you can further reduce the size of your tank. But if you go to the metal hydrides, you can further reduce the size of your gas tank. But you can see that the reduction is not very drastic, going from liquid to the solid state storage. But if you can see that this, when we want a very heavy, high weight percentage of material, hydrogen in a material, we should use the lighter element. So these are not a good lighter element. So basically, if you want to make a material with light metal, just if you take only this year, you should forget about 3D and rare earths and 5D. So then you can see that you don't have much choice of you can use this lighter element, which we nowadays we call a complex metal hydrides. If you use that kind of materials, and we can make the size of the tank with this metal hydride system with the length of magnesium. It's further back reduce. So we have those systems and we have those materials which we can use for reducing the size further down And for example, if you look at this table, they are shown many materials which called light complex metal hydride, which exist and they can have up to 28% of hydrogen if you look at lithium boron, hydrogen 4. And if any materials have more than 5 to 6 8% of hydrogen in the system, you can compete with existing oil and gas technology. So you can see there are a lot of materials which exist which have a high 8% of hydrogen. Only problem is the disruption temperature. You can see LiBH4, the disruption temperature is around 553 Kelvin. So you have to heat the system to take out hydrogen from this kind of material. So we want that the hydrogen should come out at room temperature. So we have to find the material where hydrogen can come at the room temperature, all around room. So we go on hydrogen 4 is a one good example where we can have almost 28%. Or we can take any of these alanine, which we call like sodium alanine. And here also we have 6 to 78% of hydrogen in the system. But with the disruption temperature is more than 500 Kelvin. Again, if I take this material, or I can design a new material where disruption temperature is low, or I can take this existing material and I can try use some kind of catalyst and I can reduce the disruption temperature in this material. That will be a good way to design a new material for storing and for storage. So we have looked in my system, which can be a porous system, which we call the physical system, like house. And then we have a metal hydride or this kind of system. There is a physical system. In physical system, I already discussed that ocean is very high, a very high temperature. But in physical system, it's other way around that hydrogen come out from the system at a very low temperature. So there in physical system, I have to increase the disruption temperature. But in chemical system, I have to reduce the disruption temperature. So we took about an example like the sodium method. I'm not showing you very complex material, and we have a lot of complex materials, but just to take simplicity, where you study the material and you can understand the physics or chemistry of the material. So always we test on the small system or model systems, and then we can include in the complex system. So I'm not going to show very fancy picture or very complicated picture. I took one simple example. If you take a sodium alanine, so sodium alanine, if you look at the disruption of hydrogen, and hydrogen doesn't come in a single step. They are coming out from the system in 3 different steps. The first step I get 0.78% is in 1.8, and finally the last step where I get the total hydrogen out of the system. But if you look at the disruption temperature, it's very high. So I have to reduce the disruption temperature around room temperature. It should be 25 degrees centigrade or something. So we have to think about that, how we can reduce. So then there was one experimental work where they have shown that if they add some kind of catalyst like trichloride, they can make this reaction reversible and lower the hydrogen disruption. So we have looked in the sense that if you avoid the trichloride much better, why we cannot use other catalysts which can maybe work much better than titanium trichloride. So we took this sodium alanine as an example. So just for simplicity, forget about any other group, the chemistry. If I want to take one hydrogen from this system in sodium alanine, I need 4 electron volt energy. But if I add titanium trichloride in the system, then I can reduce this disruption temperature further down to 1.9 electron volt. So hydrogen removal energy is 1.9 volt compared to 4 electron volt with and without catalyst. So it means catalyst is working and it's basically it's and showing the weakening of the energy. So hydrogen can easily release. So you can easily transfer this energy in the temperature within E is equal to kT. So then we say, okay, we try other catalysts. So that's a good thing when you're working with you. So we tried many of those catalysts. We took only the 3D metal catalysts because we don't want to use 4D and 5D material because they are much heavier. So my weight percent of hydrogen will go down. So what we done, and then we plot the hydrogen equivalent energy on the y-axis versus the different catalysts, and you can see that hydrogen equivalent energy is lowest for iron and for if you compare with the titanium trichloride. So It's almost by factor of 3. So if I use iron trichloride at the catalyst, I can further reduce the temperature by factor of 3 compared to the titanium trichloride. So this is, yeah. And then you can ask me why iron trichloride works much better than aluminum trichloride. Oh, sorry, iron trichloride works much better than titanium chloride. So you can see that if you plot the bond distances between iron and aluminum, it's lower for the iron. If you look at in this picture, my left hand side and if you see right hand side, you compare this picture. For hydrogen renewable energy, you can see the Faraday is lowest, and here the bond distance for iron is also lowest. So if we can reduce these bond distances further down, we can design a new catalyst there. Even that will be much more better than iron trichloride. So iron is cheaper than compared to titanium. So it's a good catalyst. And then we went back to our experimental colleagues, and most of these experiments are in hydrogen companies done by John Whitney. And they told me that they are using same balls for time for titanium trichloride, iron trichloride, but in half an hour time they see that titanium was better than iron. So then we have suggested them, why don't we increase the ball milling time for iron trichloride? They further grind it and more than an hour, then you can see that iron was much better than. So this is a two-way process where you can design any kind of materials and any kind of catalysts. So now these reactions are reversible. We can reduce further down the reduction temperature, and that could be even potential candidate for storing hydrogen and for mobile application. So then I took example of the metal organic framework. So I will not go much in detail because the time I will not go to the battery part, so I will focus only on this part and then I will come to and I can take the question. So metal organic frameworks are other kinds of materials, and they are nowadays and more are using everywhere, not only for storing hydrogen. If you go to even drug related, they are using more kind of materials. So it has a potential application. So if you look at the most, they are porous materials. You can a lot of ages you can store hydrogen. So again, we try to check whether, as I covered in the beginning, in the MOP system, problem is the weight percent of hydrogen is okay, but the resorption temperature of hydrogen is very low. For example, if you take group 5, in this one, the weight percentage, hydrogen is 3.38%, but that hydrogen already come out from the system at 77 Kelvin. So here I have resorption temperature and how I increase the resorption temperature in MOPS. So we use the same trick and we use the lithium trichloride as a catalyst, and we decorated our system with lithium, and then we can find that in fact lithium also works very well as a catalyst. So we done the molecular dynamic simulation and plot the wave distribution, and we can see that the shape of the peak, and we can see that I can have a resorption temperature increase from 77 to 200 Kelvin, and still maintaining 2.98% of hydrogen in the system. And even I can have a resorption at room temperature and having that to 2% of hydrogen in the system. So here the weight percentage is not important, but the idea of catalyst is working here also. So now a lot of these people who are working in terms of system, they want to focus on system. And they think that it's easy to increase the resorption temperature rather than increasing the resorption temperature. So again, catalyst work in both cases, and here you in most it helps to increase my resorption temperature of hydrogen in chemical system. Catalyst can help you to reduce the resorption temperature. So both the way both system catalyst is working. So with that software, I will not go to battery, but I will just put my concluding remark here, and these are my collaborators. So I would like to take question and have a more discussion. And if you want to know about the Indian hydrogen mission, so I'm ready. Thank you very much.
Thank you very much, Professor Ahuja, for the very illuminating talk. The session is open for questions.
Professor Ahuja will be happy to take a couple of questions. Yes, Dr. Vasundhara, Mike, can you please pass the mic to?
Thank you very much for your talk, sir. Uh, I have one question. As you mentioned about this simulation work, which is very much it gives a good path for the experiment space. So for the nanostructured material, how accurate these simulations?
So when you talk about the accuracy of simulation, I'm not interested to give you numbers, a quantitative number or exact number. So we are just showing the trend. That's I can give the idea of the simulation. You should not make simulation for the numbers. What number we are predicting, what number they are suggesting. You should more focus on the trend. What trend we are getting. So I say that if you have 10 different techniques, I can tell you which is the best technique. So you take that as an indicator. Or if I say that I can reduce the disruption temperature and using this catalyst. So that is more important to tell you that okay, disruption can be reduced if you use this catalyst. But don't think that if I say that it's reduced by 100 Kelvin or 200 Kelvin or 300 Kelvin, that number is not that reliable. So only thing the computational material science give you a trend, and sometimes our numbers match with the experiment, so that's the main difference. But we are more interested to give a prediction and which direction you have to go as a chemist also. And I have not shown the example of the batteries, where we can help the people in a which is a good electrical material. So again, there also I will not put the number, but I can tell you. If you give me a two, three different material and tell me which one is better, I can tell you better. Or we can look nowadays using AI or ML. I can look at all the databases and I can make new cathode materials or anode materials for you. But again, that is also I will say you should take that also with a clear and this is again simulation and then certain methods in the experiments we have to do.
Thank you, sir.
Yeah, Dr. Aparna Chakravarti has the next question.
Yes. Very nice and very illuminating talk, sir. So I wanted to ask this: how exactly these catalysts are chosen? Like how one should go about about choosing these catalysts?
Abhi, can you repeat? I cannot hear.
So, how are the catalysts chosen? So, how do you
How the
catalysts are chosen? Yes.
Yeah.
Yes.
Yeah. So because for if you want to use for a stationary application, especially when we're talking about hydrogen economy, I don't care about weight then because it's a stationary application. So you can choose even rare earths as a catalyst. I will not mind for that. Or platinum people are using as a catalyst. It's very rare. But if you want to use for a mobile application, like you want to use in a car or in buses or online production of hydrogen, then I will use the catalyst should be lighter because I have to compete with the in the end with the oil and gas. So I want a material which can have a lot of hydrogen in the system and can absorb like the lithium boron hydrogen fluoride can talk. It can have a 28% of hydrogen. And now if I use the catalyst to decrease the disruption temperature, the catalyst, my weight percentage will go down. So I will not use, I will use some lighter catalyst. So it depends basically which application you want to use. And for mobile application, you can try to use only the lighter catalyst because of the weight concern. That's the only criteria, especially in the area of hydrogen economy.
Okay, thank you, sir. I have one more question. Like, what is the status of using machine learned potentials for these things? This one.
What is the potential of machine learned techniques for these kind of work?
Okay, actually, nowadays AI and machine learning is a buzzword. Sometimes we don't get any help, but still we are using it. So basically, what happening? I will say that in the past we call it data mining or combinatorial approach, where redesign new material using existing database and throwing some number like redesign. For example, I want to design a high temperature superconductor, which is more important, and I want that is a VCS kind of that is electron phone coupling constant should be very, very high, so that that's possible to the during temperature. So AI and ML can help you to using huge databases. Again, figure out which materials of interest for a particular application. If you want to design a cathode material with high voltage, because right now you have a material which you are using lithium cobalt, or now people have started to use LiFeTO4. You can get around 4 volt out. If you want a material, then you can get 6 volt out, 10 volt out. You can design the using AI and ML, using all the databases. And then go back to again, you have to go back to evolution calculation, like what we are taught. So sometimes what you get from AI and ML is not 100% good. So then you have to check with the initial calculation or quantum mechanical calculation, and then you can see whether what is coming out from AI and ML is the right selection. And then if you see the same kind of trend in that initial calculation, then you can put your experiment. So this is the I will say that AI is not a, you cannot use that independently, but I would say it's more like a combinatorial approach, combining this kind of approach that's
I think actually it's more like the working on the algorithm part basically. So in the back end basically it helps in optimizing the errors, basically minimizing the errors. So AI and ML directly not calculating the properties basically. It is helping you to minimize the computational time, right, and error minimization. That's the only part of the that's why Professor Ahuja has said basically it is not directly helping the guys to calculate the properties. So computation time will get reduced, right? And because it's a fast algorithm, you can do the fast calculation. So that's what it is.
And are there any more questions? Yes, yes.
Yeah, please.
Dr. Chapro has asked a question.
Professor Ahuja, it's nice seeing you here, and congratulations for leading two of the premier institutions in our country. Well, I wonder whether you're setting up some experimental facilities for testing the simulations at Gopal or Guwahati.
again, Ravi, I cannot hear. Can you repeat?
Yes. Are you setting up any experimental facilities in IIT Guwahati to substantiate the theoretical calculations? So, some experimental facilities in this direction.
He's not able to catch this. Yeah.
Can you repeat again, Ravi?
Yeah.
I cannot hear.
Yes. Are you thinking to set up any experimental facility in IIT Guwahati in this direction?
Oh.
Yeah.
Actually, there are groups working here, and but Roper, I know that there's a group working here. So, of course, most of this hydrogen value is coming to IITs again. So, but I have not seen an application from IIT Guwahati, so I don't know. Maybe the people in the chemistry department they are working on hydrogen. That's a good area, and they should take also in IIT Guwahati. But other IITs I know, for example, IIT Bombay, they are coming up, and then IISER Pune is also coming up there within this area. IIT Jodhpur also, and IIT Delhi also. But I have not seen any application from IIT Guwahati. But I have to discuss here with the chemistry department, or maybe they are working on hydrogen. So if they are not working, they should work because this is the upcoming area where they should work. That's the issue. I'm not sure I answered your question right. There's a problem to listen from your side. The sound is not coming properly.
Yeah. I think Dr. Chapel is satisfied with your answer, as I see. And are there any more questions? One more question from the back. Yes. We have to pass the mic to her. But Professor Ahuja, are we audible to you? Rajiv, can you hear us?
No, I cannot hear clearly from you. That's my problem.
Actually, the electrolysis process for hydrogen production will require some energy. So there are several scopes in photovoltaics to drive the system electrolysis. So then the full things will be clean and green. And what are the scopes in future to in this area that photovoltaics are actually driving the hydrogen production. And the storage part also, we are trying to, if it is the load where we can storage, so there will be any kind of regulation and automation required from electronics part so that we can sustain the energy production. That is.
Because if I understand you, because regarding the storage, and now if you talk about storage, I told you that India is mostly going to the gaseous storage, and they are talking about the different type of cylinders, type 1, type 2, type, now we are talking about type 4. And so then we are using very high pressure, 700 bar is a big pressure for hydrogen. So we have to find a materials where hydrogen, because you know the hydrogen is very nasty, so it interacts with the materials, the boundary of the cylinder, and it creates a cracks and all those things. So people are talking about the composite materials also, the carbon-based fibrous materials, carbon fiber materials for storing hydrogen. So this is the situation right now in the gaseous storage, and so now they are talking about the cylinder, big cylinders, not the small cylinders. So material is very important because otherwise my cylinder is very heavy. So now they are making this composite carbon-based material, and but the carbon-based material also not very safe actually. Maybe you know the recent accident in one of the submarine having a carbon fiber as a cylinder, and that busted, and you see that all the 7 people in the submarine they are. So again, the materials developing is rendered also not easy because hydrogen under pressure is a bomb. So that's the one standard people are looking, but there are now standardization. What kind of cylinder has to be used for the mobile application? For the stationary application, I don't worry too much about it. I can produce hydrogen on board and or not on board. As a stationary, like I want to make a hydrogen-based generator in the backside of my home, I can generate hydrogen, I can use that. I don't need to store it. And there I don't have to worry about the much weight also. So I always say that if hydrogen economy is going to work, it will be going to work in either a submarine or an ocean. Their weight is not a problem. So you can, if you, I mean, how we use the seawater, how we can do the desalination of seawater, and we can produce hydrogen on board and we can drive all those ships. So that's the future. So since I cannot hear you properly, so this is my summary. Otherwise, you can write to me and we can have a discussion also. And if you are applying for Hydrogen Valley project and if you want to be a collaborator at IIT Rockford, you are most welcome.
Yeah. So if there are no more questions, please join me in thanking Professor Ahuja for the very insightful and wonderful talk, and also for sparing his valuable time for us today in the morning. Thank you, Professor Ahuja, very much. Thank you, Rajiv.
Thank you, Abhi. And thank you, Anurag.
Yeah. Thank you so much, sir, for joining us during this Candy 2023. We'll see you another time in physical mode. We'll be here in Bali. Thank you so much. One and all. So we are just closing the session. So thanks to the chair, Professor Abhi, for conducting the session. And you all are invited for the high tea. Thank you, sir. You can log off now. Yeah. Welcome.
Thank you.
Back to convention center, session will be there. We can also take high. Yes.